One unique feature of NEI's STEM EBIC system is the ability to independently collect two different EBIC signals from your sample at the same time. In this video, we're going to talk about why that's important, and namely because it gives us the ability to distinguish between the two different EBIC modes in situations where both are present. Here's a diagram of a device exhibiting standard EBIC current where we're connected to two separate EBIC amplifiers. And you'll notice that for every electron that goes into the amplifier at the left, you're going to collect a corresponding hole in the amplifier at the right. A more accurate depiction of what goes on is that as the electron beam scans, you basically always are getting CBIC signal, even when it's too small to really see under the standard EBIC contrast. That CBIC is more or less always there. So it can be difficult just from looking at bright or dark contrast to understand exactly what's going on and exactly what signals you're looking at. Well, as it turns out, you can actually use just basic image math from EBIC acquired on two separate electrodes to distinguish between the two. So for example, if we add the signal from these two EBIC amplifiers, the electron that goes into one amplifier from the standard EBIC annihilates with the hole that goes into the other, and what you're left with is just the CBIC signal. Conversely, if you subtract these two signals, you subtract out all, if not some, of your CBIC signal, and what you're left with is basically a doubling of the magnitude of your standard EBIC. So now I'm going to show a very quick example just to prove that this works and that it works well. This is a strip of GST between two tinitride electrodes, and this is some unpublished work from Andy Chan at UCLA. If we connect an amplifier to the left electrode, we can see that there is some bright and dark signal at each of these interfaces, which is presumably from the Schottky barrier at the metal semiconductor interface on both sides. If we connect to the right electrode, we can see something that approximates an inversion of that signal. And now let's do some image math to see what happens. So if we add these two channels together, the bright and dark patches at the interfaces go away, and what we're left with is just a secondary electron image of our device. And so this kind of confirms that the signal we were seeing at those interfaces was in fact due to standard EBIC, most likely due to the Schottky barriers present at each of those interfaces. We can subtract those two channels, and what's left here is just the standard EBIC signal. So now that I've hopefully convinced you that adding and subtracting these channels work, I'm going to just show one more example where this actually comes in critical for understanding the device physics that's going on while we're imaging. All right, here we're looking at two valence change resistive memory devices, and in each case we have a platinum and titanium electrode separated by a layer of hafnium oxide, and we're measuring EBIC in the lower platinum electrode while we're applying a small bias to the upper titanium electrode. The main difference between these two pairs of images is that the upper two electrodes are much closer than the lower two electrodes. On both of the EBIC images, there's a bright fringe that shows up at the edge of the platinum, but it's difficult to say exactly what's happening, and even if it's the same thing occurring in both of these images, just from looking at this one fringe of bright contrast. As it turns out, at the same time we're acquiring EBIC on the platinum electrode, we are also acquiring EBIC from the biased titanium electrode. Now, these titanium images don't seem on their own to give much more information than the platinum EBIC images, but if we add them together, things start to look much clearer. So in the sum of the upper pair of images, we see that this bright fringe has basically disappeared, whereas in the lower sum image, the bright fringe remains. And what this tells us is that for the upper images, this bright fringe was caused by standard EBIC. In other words, you have two electrodes that are close, you're applying a bias that generates an electric field, you separate electron hole pairs, and that produces your standard EBIC signal. However, in the lower sum image, that bright fringe remains, and that tells us that it's not due to some electric field effect, and that it's actually due to CBIC, which indicates that this is corresponding to a local conductivity change. So this is just one instance where it's critical to understand what the different types of EBIC you're looking at are in order to really understand what physics is happening in your field of view. Here, I'm just going to leave some more information if you'd like to learn more about STEM EBIC. Please check out some more videos on our YouTube channel. And if you have any questions about our STEM EBIC system or about EBIC in general, please send us an email.